general complex exponential signals already we have seen in last video. The general discrete time complex exponential can be written and interpreted in terms of real exponentials and sinusoidal signals. Real exponential signals and sinusoidal signals. Specifically, if we write C and alpha in polar form. C and alpha. Why is C equal to mod C e power j theta, and alpha is also in polar form. Alpha equal to mod alpha e power j omega naught. Then C alpha power n. Okay. So mod C mod alpha power n cos of omega naught n plus theta plus j mod C mod alpha power n sin omega naught n plus theta. For mod alpha equal to 1, real and imaginary parts of complex exponential sequence are sinusoidal. For alpha is less than 1, for alpha is greater than 1, they correspond to sinusoidal sequences multiplied by a growing exponentials sinusoidal signals here. Okay. Growing compared to here growing because growing exponential signals. Like this, when mod alpha is less than 1, the corresponding sinusoidal sequences multiplied by decaying exponentials. Here exponential decaying. So that's why there is sinusoidal signal also decaying discrete time sinusoidal. Here in A growing discrete time sinusoidal signals. Then periodicity properties of discrete time complex exponentials. Many similarities between continuous time and discrete time signals. Like that, number of important difference also is there. One of these concerns the discrete time exponential e power j omega naught n. The following two properties of its continuous time counterpart e power j omega naught t. First one is the larger magnitude of omega naught. The higher is the rate of oscillation in the signal. The larger the magnitude of omega naught, higher is the rate of oscillation in the signal. The signal higher oscillation. The higher oscillation rate is higher. Rate of oscillation is higher in the larger magnitude of omega naught. Second one is e power j omega naught t is periodic for any value of omega naught. Any value of omega naught is that periodic. First one is the larger magnitude of omega naught, the higher is the rate of oscillation of this in the signal. Signal oscillation rate is higher due to larger magnitude of omega naught. In the section we discussed the discrete time versions of both these properties, and as we will see there are definite difference between each of these and its continuous time counterpart. The fact that First of these properties is different in discrete time, is a direct consequence of another extremely important distinction between discrete time and continuous time complex exponentials. Consider the discrete time complex exponential with frequency omega naught plus 2. From this e power j omega naught t we have to change for t is for continuous time counterpart. So where n we have to replace for t for discrete time complexes. So here e power j for this omega naught plus 2y. That's why with the frequency. Consider the discrete time complex exponential frequency uh, omega naught plus 2 pi, then instead of t here n will come due to discrete time complex exponential discrete time. So e power, so here now simplify this, then we will get e power j e power j e power j 2 pi n first, okay, then e power j omega not n, this one and this one. So equal to, here we will take this one only, e power j omega not n, e power j 2 by n will not consider j 2 by n. Here we will count the e power j omega naught n, this one only, okay. So from this equation we see that exponential at a frequency sigma, omega naught plus 2 pi, omega naught plus 2 pi is the same as that at the frequency omega naught. That is exponential at the frequency omega naught plus 2 pi is the same as that of at the frequency omega naught. We have very different situation from the continuous time case, in which the signals e power j omega naught t are all distinct for distinct values of omega naught. In discrete time, these signals are not distinct, but in continuous it is distinct, but here it is not distinct, as the signal with the frequency omega naught is identical to the signals with the frequencies omega naught plus 2 by omega naught plus or minus 4 pi and so on. In continuous time case, signals e power j omega naught t are all distinct for distinct values of omega naught. But in discrete time, these signals are not distinct, as the signal with the frequency omega naught is identical to the signals with the frequencies omega naught plus or minus 2 by comma omega naught plus or minus 2 by and so on. Therefore, in considering discrete time complex exponential, we need only consider a frequency interval of length 2 pi in which to choose omega naught. In discrete time complex exponentials, we need to only consider frequency interval length of 2 pi only, in which to choose omega naught. Although according to equation this 1.5 1 e power j j of omega naught plus 2 pi n 2 pi of n equal to e power j 2 pi n e power j omega naught n equal to e power j omega naught n. According to this equation, any interval of length 2 pi will do. On most occasions we will use the interval omega naught in between 0 to 2 pi, that is 0 is less than or equal to omega naught, that omega naught is less than 2 pi, or the interval omega naught is in between minus pi to plus pi, that is minus pi is less than or equal to omega naught is less than equal to pi. Here open interval, here closed interval, here open interval, here this open interval, here closed interval. Okay, because of the periodicity implied by the equation 1.51, the signal e power j omega naught n does not have a continually increasing rate of oscillation as omega naught is increased in magnitude. Periodicity implied in this equation. Periodicity implied. The signal e power j omega naught n does not have a continually increasing rate. Does not have a continuously increasing rate of oscillation as omega naught is increased in magnitude. Omega naught is increased in magnitude, but does not have continuous increase in the rate of oscillation. Rate of oscillation is not increasing. Rate of oscillation is not continually increasing, but omega naught has increased in magnitude. In this magnitude increasing this omega naught. Rather, as illustrated in figure 1.27, as we increase omega naught from 0 to omega naught increasing, we obtain signals that oscillated more and more rapidly until we reach omega naught equal to pi. That is, we increase now the omega naught from 0, that is magnitude increasing. We obtain oscillations, signals that oscillate more and more repeatedly. This one more and more repeatedly until we reach that omega naught equal to pi, up to pi. This one not, this one is continuous. Continuing up to pi. Then as we continue to increase omega naught, then omega naught increasing, what will happen? We decrease the rate of oscillation until we reach omega naught equal to 2 pi, then which produces the same constant sequence as omega naught equal to 0. Therefore, the lower frequency, that is slowly varying, discrete-time exponentials have values omega naught near 0 to 0, 2 pi and any other even multiple of pi, while the high frequencies corresponding to rapid variations are located near omega naught equal to plus or minus pi and other odd multiplies of pi. Note in particular that for omega naught equal to pi or any other odd multiple of pi, e power j pi n equal to e power j pi power n equal to minus 1 by n, 1 power n, so that the signal oscillations repeatedly, changing signs at each point in time, as illustrated in figure E. First, tan